Today we're going to have a look at a slightly more complicated version of a application of a maximum or minimization problem. So a square sheet of cardboard has side length of 3 meters. A square side length X is cut from each corner and the sides are turned up to form an open topped rectangular box with a square base. Let V cubic meters be the volume of the box. Express V in terms of X. Ready? So just as a nice little reminder, we can see here that these dotted lines that I'm drawing in are where the folds get made. So these little rectangles end up being the little rectangles on the side, and the bottom rectangle is the rectangle that is right on the bottom here. So the question is, what is the area of this, or the volume of this? So it's going to have some, let's call it, let's not call it X, let's call it some kind of side length S. Alrighty, so this side length S is going to be here, and here, and here, and here. And so the volume of the whole thing is just S times X, or S squared X. The real question is, what's S equal to? Well, since the whole length is equal to 3 meters, and we're taking off 2 lots of X, it's 3 minus 2X. So now we can substitute that in here, and we get 3 minus 2X squared X. Now it may be useful to leave it in the factorized form for later. However, we're going to be doing calculus in a moment, and so best to expand out these brackets. So let's do that. Alrighty, so expanding those first brackets, we get 9 minus 12x plus 4x squared, and expanding the outer brackets, we end up with 9x minus 12x squared plus 4x to the 3, which is exactly what we needed to show for part B. So that's part B answered as well, right there. Obviously, we should just reorder it so it looks right. Now for part C, it asks us to determine the domain of the function. Alrighty, so let's just imagine some extreme cases where we are playing with this box. What if x was equal to 0? What would happen? Well, it means that we wouldn't cut out any of the box, which means that the whole box would just be a flat piece of card, which means you wouldn't be able to fold it, so it would have a volume of 0. So x equals 0 is going to be our lower bound. Now let's imagine the other one, where x gets really, really big. Well, at a certain point, as x gets bigger on this side, x is also going to get bigger on that side. All right? So what's the eventual stopping point? Well, the eventual stopping point is when these two cuts actually meet and we cut out the entire shape, because each of the cuts get too big. How big is that? Well, you can see we've got 3 meters and we're dividing it into 2, so 1.5, x equals 1.5 is going to be our upper bound. So the domain of V, ends up being x is in bigger than 0 and less than 1.5. Because in those two cases, you either A, end up with no more cardboard because you cut it all away, or B, you didn't cut any cardboard and so you can't fold it. So now we're up to D and E, which is going to be using calculus to actually solve for the maximum volume. So this is our volume function, and we are trying to maximize. Well, we've already worked out the two domain points, and we already know that those volumes are going to be 0. So instead we can worry about just looking for when dv dx is equal to 0. So first of all, let's work out dv dx. 12x squared minus 24x plus 9 is our derivative function, and we can sub in dv dx is equal to 0. Now in order to solve this, we're going to need to factorize out the factor of 3. This is a slightly trickier quadratic, but we can still use a t-chart. Multiplies to 12, adds to -8. The solution, which is -6 and -2. So, since it is not a monic function, there's a 4 in front, we're going to need to split and factorize bit by bit. So split the middle term into -6x minus 2x, and then factorize bit by bit. And then notice that we can now factorize out the 2x minus 3, and we are left with this, which by the null factor law means we have two solutions. Either x is equal to 3 on 2, which is 1.5, or x is equal to 1 on 2, or 0.5. Now, we worked out before that the domain of the function is between 0 and 1.5, not including 1.5. So automatically 1.5 is out. This cannot be a solution. Therefore, the only stationary point that we have is 0.5. Well, it's the only potential, is a potential maximum. However, it is a guaranteed maximum just because we know that the function is positive between 0 and 1.5. Otherwise, you'd be getting negative volumes, which doesn't make any sense. So this is the maximum. Now that we know what x is, we also need to work out what the dimensions of the box are going to be. So let's go back to our picture. Alrighty, so we know that 0.5 is going to be the height of this box after we do the cutaway. And since we're taking 0.5 off twice, that means this inner is going to be 2 meters. So the eventual box we're going to end up with after folding is going to have dimensions 2 by 2 by 0.5 meters. And the volume of that function, well, we could use our original formula, or we could just use 2 by 2 by 0.5, which is just 2 cubic meters. Alrighty. Is the maximum volume. Alrighty, so 2 cubic meters is the maximum volume with dimensions of 2 by 2 by 0.5 meters. Alrighty, last part of the question is just to do a quick sketch. We actually have all of the information we need. So the last part is just to sketch phi against x, showing all key features. Now we've actually worked out pretty much everything that we need to know. We know that the maximum happens at 2, and we know that the volume at that point, at 0.5, has a volume of 2. We also know that at 1.5 the volume is 0, and at 0 the volume is 0. So that means we have a function which increases and then slowly decreases until it hits there. You'll notice I've used circle for the two endpoints because, as we know, those are going to be not included in the function because you can't, well, you'd end up with volume of 0, which is not very interesting. Alrighty, so that ends up being our sketch. Alrighty, thank you for watching. See you in the next one.